Hello everybody, hope all of you are doing good. Today we will talk about maximum likelihood estimation and expectation maximization algorithm. So we have already talked about in class about knife-based algorithm, which is a probabilistic model following classification. So any probabilistic model such as Bayesian networks, they can be used to model biological data. Just because they can learn from the observations, they're very popular, they're robust and they're fast, of course. But again, there might be a problem when we are doing work with a large set of data. There may be times when we do not have complete information with us. So what is meant by not having complete information and incomplete information? Like we can have certain missing values, like in medical diagnosis, we may not have sufficient patient history to reach a conclusion about the patient's conditions. So in this regard, expectation maximization algorithm enables parameter estimation in a probabilistic manner with incomplete data. To understand how expectation maximization algorithm works, we first need to have some idea about maximum likelihood estimation. So let us talk about a coin flipping experiment. This is a very popular experiment that was conducted to make people understand about expectation maximization algorithm. Now let us consider a simple coin flipping experiment in which we are given two coins A and B of unknown biases. That is, when you flip coin A, it lands on head with probability theta A. So of course the probability of having landing on tail would be 1 minus theta A, and the same goes for coin B as well. So our goal is to estimate this unknown biases by repeating the procedure 5 times of randomly choosing one of the two coins, of course with equal probability, and then perform 10 independent coin tosses with the selected two coins. So in total we would have 50 coin tosses. So 10 times we are tossing, 10 times we are doing coin tosses, and we are repeating this 5 times. So of course we would have 50 coin tosses. So during this experiment we need to keep track of two very important vectors, x and z. So what is x over here? X is the repetition of the procedure 5 times, and z is, I'm extremely sorry, x is the number of heads observed during this 5 coin tosses, and z is the identity of the coin used during the ith set of tosses. So what does it mean? So x would represent, of course, the number of heads, and z would represent which coin is getting tossed. So parameter estimation in this setting will have a complete data case so that all the values would be known to us. So how does that work initially? I will show you with the help of a diagram. See, this is one diagram, but before that we need to know how we would estimate the probability of a coin toss. So that can be done by using maximum likelihood estimation. So a very simple way to estimate theta A and theta B, that is our unknown biases as talked about in the previous slide, would be theta A is equal to number of heads using coin A divided by total number of flips using coin A. Similarly, theta B would be number of heads using coin B divided by total number of flips using coin B. So this intuitive guess of estimating theta A and theta B is, in a broader sense in statistical literature, is known as maximum likelihood estimation. That is, it tells us the maximum probability or the maximum estimation of a particular event happening. Okay, so let us now look at this very important diagram, which would help us to understand how we can find out the value for maximum likelihood estimation. So we have two coins, as I have said, A and B. As you can see, the first coin that has been flipped is coin B, and coin B is, when flipped, lands on head 5 times and lands on tail 5 times. Again, for coin A, when coin A is flipped for the second time, it is the number of heads is 9 and number of tails is 1. So these goes on for 5 times. So finally we would have for coin A 9 head 1 tail, 8 head 2 tail, 7 head 3 tail, and for coin B we would have 5 head 5 tail, 4 head 6 tail. So if we add up all the heads and tails for the individual coins, we would see that for coin A, we would have 24 heads, that is 9 plus 8 plus 7 is 24, and 6 tails, 2 plus 1 plus 3. Similarly, for coin B, we would have 9 heads and 11 tails. So then what is theta A? Theta A would be the, as we have seen in the previous slide, number of heads using coin A, so that is 24, divided by total flips of the coin, that is 30. So that would give us 0.8. Similarly, for coin B, what we get for maximum likelihood estimation is 0.45. So this is pretty simple and straightforward, I believe. So this is how, when we have complete set of data, that means we know which coins have been flipped, how many times they're landing on head, how many times they're landing on tail. We have a complete scenario. We have been able to estimate the biases theta A and theta B. So I hope you have understood what is theta A and theta B. I would just go back again and see and tell you what is theta and theta B. So theta and theta B again is the probability of landing on head, that is theta A, and the probability of landing on tail would be theta B. So, okay. Now, as I have said that expectation maximization algorithm works with incomplete data. So, consider a case in which we have the recorded head counts X, but we do not know which coin has been tossed. Okay. So, this unknown variable is known as latent factors. Okay. So, in here we would call Z as hidden variables or latent factors. So, parameter estimation in this new setting would have an incomplete data case. So, see, this time we will not be able to compute the proportions because we do not know which coin has been used for which set of tosses. But if we can have some kind of a method in which we would have the provision of completing the data, then we could again use maximum likelihood estimation with complete data. That means we were having right now incomplete data, so we are not being able to apply maximum likelihood estimation directly. So rather we would try to create complete data with this incomplete data so that we can directly apply maximum likelihood estimation. So then what we need to do? One very important scheme that can be applied over here is, so we can have, starting from the initial parameters, that is theta A and theta B. So we have a hat over here, that means we have this estimated parameter, right? Whenever we have a hat on any value, we know those are estimated parameters. So what we would do is, starting from some initial parameters, we would try to determine for each of the 5 sets whether coin A or coin B was more likely to have generated the observed flips. Then assume that our guess is correct, we would apply maximum likelihood estimation to get the next parameter, and we would keep on repeating these steps until we have got a final result, until we have converged. So as the estimated model improves, so will the quality of the resulting completion. Expectation maximization algorithm actually works on this knowledge. So this is a refinement of the previously mentioned basic idea. So what we do over here, expectation maximization algorithm computes probabilities for each possible completion of the missing data using the current parameter. So then after this has been done, these probabilities are used to create a weighted training set consisting of all possible completions of the data. Finally, maximum likelihood estimation or a modified version of it is used to deal with weighted training example so that we can get some new parameter estimates. So by using weighted training example rather than choosing the single based completion, the expectation maximization algorithm ensures the confidence of the model in each completion of the data. So we can now summarize expectation maximization algorithm in a way that it alternates between an expectation step and a maximization step. So what we do over here, we try to guess the steps of probability distribution over completions of missing data given the current model, and then try to re-estimate the model parameters using the previously calculated completions. So the name E-step comes from the fact that we are not explicitly calculating any probability distribution, but we are trying to compute expected sufficient statistics. Similarly, the M-step actually helps with the maximization of the expected log likelihood of the data. Okay, confused, right? This sounds very hibby-jibby. So let us now try to understand the steps of expectation maximization algorithm with the help of a numerical example. So let us first now go through the steps just once more. So EM starts with an initial guess of the parameters. EM is your acronym for expectation maximization algorithm. In the E step, a probability distribution of a possible completion is computed using current parameter. In the M step, new parameters determined using the current completion. After several repetitions of the E step and the M step, the algorithm finally converges. Now, see, in the previous example, when we are talking about maximum likelihood expectation, see here the names of the coins are given. See, we can see the first coin flipped was B, second was A, third was A, fourth was B, fifth was again A. But if we now look at this current scenario, only we know that heads have been flipped, tails have been flipped. How many heads have been flipped, how many tails have been flipped, but we do not know which coin has been used to flip this, so to get this data, So how do we find out which coin is more likely, or how do we find out the final biases, which was pretty straightforward for maximization algorithm. Pretty straightforward for maximum likelihood estimation by using this straightforward formula of theta A and theta B. So what we do over here is, please listen to me carefully. Okay. So initially we try to guess some biases. So our initial guess would be theta A is equal to 0.6 and theta B is equal to 0.5, as has been marked with blue circle in the figure, if you can see. So the likelihood of the corresponding set of 10 coin tosses produced by the two coins need to be calculated, which should be normalized to add up to 1. So before going into that, just see, so 0.45 plus 0.55 is 1. 0.8 plus 0.2 is 1, 0.73 plus 0.27 is 1, and so on and so forth. So how do we calculate these values? I'm going to explain next. So what we do is, we try to find out the estimate probability of K out of 10 tosses of coin Z in the ith toss yielding head. So we know what is binomial coefficient. So if we just try to find out that, our straightforward formula is, the probability would be, there are 10 tosses. So, and then what is the probability of finding out each? That is given next. So see, understand one thing. If we go back, let's say for the second toss, we see there are 9 heads and 1 tail. So since we do not know which coin has been tossed, we can easily say that it can be either A or either B. So if it is A, then also 9 heads had been tossed, 1 tail has been tossed. If it is B, then also 9 heads have been tossed, 1 tail has been tossed. So the binomial coefficient would be the same for both of the coins. So we do not need this part in the entire equation. We would try to find out the value using the rest part of the equation. So how do we find out that? See, theta A to the power 9, that is K is 9 over here. So you can understand that if we would have taken 10CK, that is the first part of the equation, the answer would have been 10C9 for both PAK and PBK. So it doesn't really matter. So we drop down this part, and what we are left out with is theta A to the power 9, where theta is A is equal to 0.6 and 1 minus theta A to the power 10 minus 9, and that approximately gives us 0.004. Similarly, putting in the values of theta B is equal to 0.5, we get the probability to be 0.001. So now if we apply our normal maximum likelihood estimation, what we get, we know the total value divided by the individual value divided by the total value. So that would give us 0.8 and 0.2. So that is exactly what we have got in for the second coin toss. Similarly, you can find out that if you calculate by yourself, you can do that of course at home. You can see that the values we would get are 0.45, 0.55, 0.73, 0.27, approximate values of course, 0.36, 0.65, 0.35, 0.65 and 0.65 and 0.35 respectively. So this part I think is done. Now, so we have understood how we can find out the probability values, but then if you look at this figure, we see for coin A, the expected values are 2.2 head, 2.2 tail, 7.2 head, 0.8 tail, 5, that is I'm talking about coin A right now of course, similarly for coin B also. So you may wonder from where this 2.2 to 7.2, 5.9, from where all these values are coming. So that is what I'm going to explain next. Now we have calculated the proportion, that is what would be the proportion of coin A and what would be the proportion of coin B. So the proportion of coin A is 0.8 and proportion of coin B is 0.2. So since we have calculated that, what we are going to do is, we have 9 head tosses and we have 1 tail toss, right? So we have seen that we have 9 head tosses and we have 1 tail toss. So what we are going to do right now is, we are going to multiply this factor with the tosses. So 0.8 into 9 would give us 7.2 and 0.8 into 1 would give us 0.8. So this is added to the column for coin A, and again a contribution of 0.2 into 9.1 which would give us 1.8 and 0.2 is added to the column for coin B. See, it has been marked as green circle in the figure. So they are actually the weighted contributions to the actual result, which has been weighted in proportional to the current buyer's estimate. So if I go back to the steps of EM algorithm, you see in step 2 it has been clearly mentioned that in the E step, a probability distribution over possible completion is computed using the current parameters, which is 0.8 and 0.2 for the second token cost, 0.73, 0.27 for the third token cost, and so on and so forth. After that, the counts shown in the table are the expected numbers of heads and tails according to this probability distribution, which is 2.2, 2.2, 7.2, 0.8, 5.9, 1.5, 1.4, 2.1, 4.5 and 1.9. So these are the expected values, and 0.8, 0.2, 0.73, 0.27, 0.45, 0.55, they are the probability distributions. So what we need right now are the weighted results. So together you see they would add up to 9 and 1, because see what we want the weights to be normalized to 1, right? So if you see 7.2 plus 1.8 is 9 sorry, and 0.8 and 0.2 would give us 1. So that is how we get back our 911, that is our initial coin tosses, that is 9 heads and 1 tail. So thus the more likely it seems that according to the current buyer's estimate that this row was actually produced by coin A. So why do we say that? Because see, for coin A the contribution is 7.2 and 0.8, and for coin B the contribution is 1.8 and 0.2. So which one is more probable to happen? So we can actually say from this value that probably the second toss was made by coin A and not coin B, because column of coin A for this particular toss has a higher weighted value. Okay, now we have understood, I hope we have understood how the second step works. Now we would move forward and go to the third step. Sorry. So if you go to the third step, what we are doing over here is exactly what we have done for maximum likelihood estimation. Okay, this figure is not very visible over here, I believe. So I would just go back to the main figure. If you see over here, after completion of step 2, that is after completion of calculation of all the probabilities and the weight, finally what we have got for coin A is head is 21.3 and tail is 8.6. Similarly for coin B, what we have got is head is 11.7 and tail is 8.4. So the way we have calculated maximum likelihood estimation, we would do it over here, because now we can say we have a complete set of data, because initially we started with nothing. We did not have any inkling of whether the coin tosses were made by coin A or coin B, but at least as an intermediate part, we have some idea of the weighted factors of coin A and coin B. So now we can apply our maximum likelihood estimation. So for coin A, the bias theta A can be calculated as 21.3, that is the head flip for coin A, that is 21.3, divided by total number of flips, that is 21.3 plus 8.6. Similarly, for coin B, the bias would be theta B, which is equal to, in the numerator we would have the number of flips for head, that is 11.7, divided by the total number of flips, that is 11.7 plus 8.4. So see, if you just look at the figure, it's pretty straightforward. Initially you are guessing the parameter, then you're applying the expectation step where you are calculating the probabilities and the weighted values. In the third step, we are doing the maximization step where we are applying maximum likelihood probability by doing the division between the number of head flips divided by the total number of flips for both the coins, right? So this is what our step 3 is all about. So we would keep on doing all these 3 steps, 1, 2 and 3 we would keep on repeating the steps 2 and 3. 1 is for initial guessing, sorry for that. So we would keep on repeating steps 2 and 3 till the algorithm converges, right? So in this case, that is theta 10. So finally, we would have the value in theta 10 as 0.8 and 0.52. So if I go back to maximum likelihood estimation, you would see over here our theta A was 0.8 and theta B was 0.45. So the result we have got right now using expectation maximization algorithm is pretty close to what the actual value is. So now we have a complete set of information with us, right? So we can easily say that what is our maximum likelihood probability, what is our value. So now we can say for sure that we have been able to compute some value which is not about incomplete data anymore. So it behaves as if we are working with a complete set of data. So in conclusion, what we can say is expectation maximization algorithm is a natural generalization of maximum likelihood estimation for incomplete data case. So we started with incomplete data where we did not have any inkling about whether the coin toss was made by coin A or coin B, and we were trying to understand how we can estimate the final value, right? So in particular, expectation maximization attempts to find the parameters theta that maximize the log probability for the observed data. So hope you have understood what has been taught today. If you have any doubt, any question, I have given my mail ID in the first slide. You can mail me, or if you have my number, you can call me. I'm always here to help you out. Hope you are doing very well, and I hope you stay safe in this situation, and please stay home. So all the best for your future. Thank you.